So here you see our first problem as a 3D description of forces. And as always, we always want to read the problem statement first. And in this case, we want to describe the 200 Newton force as a Cartesian vector. What is a Cartesian vector? A Cartesian vector is something that says F is equal to Fx I hat plus Fy j hat plus Fz k hat. And so this is what we're looking for now. No, nothing more, nothing less. Notice that we are given these two angles here, which usually in the classroom I would ask you now to think about like how to deal with that and so on. But here I'm just solving it for you. So this clearly is beta because it connects the y-axis to the force, and this is clearly gamma because it's between the force and the z-axis. That means we're missing alpha. So keep in mind that when you miss alpha, you have to determine that one first. Don't get me wrong, there are other ways to find this. You could use Pythagorean in 3D to really arrive at the last component here by projecting it first down here and so on. But it's all unnecessarily complicated. So what we're trying to teach you here with this problem is to really use these directional cosines to arrive at a proper, precise, quick answer. So let's get started and let's define how we get there. Maybe first we'll start by rewriting this in terms of the 200 here so that we know where we're going. So in fact, in this case, my F force would be nothing else than 200, in this case Newton, multiplied by the cosine of alpha I hat plus the cosine of beta j hat plus the cosine of gamma k hat. And that is what I have to complete now. Once again, I'm missing alpha. How do I find alpha? By knowing that cosine square alpha plus cosine square beta plus cosine square gamma is equal to 1. So all I have to do now is rearrange it for alpha. So I do that in steps here so that it's easier to follow. So 1 minus cosine squared beta minus cosine squared gamma is equal to cosine squared alpha. So now I have to get rid of two things. I have to get rid of the square of the cosine and the cosine itself. The square is actually easy to get rid of. In fact, you know this, right? Sometimes students are confused because now the square is applied to a function rather than like a number, but it's just the same. You just take the square root of this term and then you remove the cosine by taking the inverse. So ultimately, you end up with alpha being equal to the cosine inverse of this whole term square rooted. So 1 minus cosine square beta minus cosine square gamma, and that is the whole thing. Now all I have to do is replace these values. So beta in this case is equal to 60 and gamma is equal to 45. And if I now complete this, what you will find is that alpha is equal to 60 degrees as well. Now, let me give you a word of caution here. Sometimes, specifically in your homework, you will find that a force is not in the first octant, right? So you now have 8 octants in a coordinate system because it's 3D. And that means that this angle here can take on any value between 0 and 180. And when you solve these type of equations, they are really repetitive through 90 degrees, right? Keep that in mind from your basic trigonometry. You can find the real reason of that in the very first or in the very zero lecture in this class. So your calculator might trick you if your force goes into a different direction or is located in a different octant. Be very careful about this. Don't believe your calculator immediately. It's always best to draw a sketch first and draw that sketch as true as possible so that you really have a solid interpretation of in which direction that force is acting. Here is the very first introductory problem, so we don't have to worry about this. This is true. This is the answer that our calculator would give us, but this is not always true. Be careful when you deal with trigonometric functions. All right, so now we can express our force. Let's do that next. So I can now say that F is nothing else than 200 Newton times the cosine of 60 I hat plus cosine of 60 J hat plus cosine of 45 K hat. And if you calculate that out, which you always have to do, you will find that we're looking at 100 I hat plus 100 J hat plus 141.4 K hat. And that, of course, deserves a unit. And also, it is really an answer. So therefore I have to double underline it. And now you may be surprised because you probably think, we always have to give 3 answers, which I will do for you. However, notice that the problem statement actually asks you only for the Cartesian vector description. So it's this guy here. And the 200 is already given. So this is the magnitude. And the angles are also already given. So in this case, you were only asked to produce this answer. So I actually do not have to give you any other answers because the magnitude is already provided within the problem statement, and then alpha, beta, and gamma are already available. That means we are done with this problem and we can move on to the next. Let's do that. So now that we have an initial understanding of 3D vector description and the possible traps that we could fall into with the angle description in 3D, we can actually move on to solving real engineering mechanics problems. So you see actually 2 problems here, and if you read the problem statement, it suggests that you should pick the more complicated one to determine the resultant force that is acting on either of the eye bolts or the hooks, and you should describe the directional angles. So my experience in the classroom is that this problem here on the right is actually more complicated to students. And therefore, in the classroom, we usually solve this one first. And then when we have more time, we also solve this one. This, however, is easy because everything is already given to you in vector description. Whereas here, you really have to find your own vector description. So you have to turn this force into ijk and this one as well into ijk. So I will focus on this one now. Let me zoom in and let me talk to you about the way this picture is really described to you, because students often confuse this or have a hard time initially to interpret 3D pictures. And this is something some of us have and some of us don't have yet, but everybody who's in the engineering program is capable of getting there. Some have to practice this harder than others because you will need a solid 3D understanding. And what I'm talking about is these planes here. Problems in engineering are often described by these planes and with angles relative to each other. You need to develop a feel for how forces act, and you need to be able to see somehow in your head what 3D system is acting there. Of course, here in this class, we make it very easy comparatively for you to understand where they are, like I said, by these shaded areas and by the description. In the real world, that's of course a little bit different, and there you really need a good 3D understanding. So let me introduce to you this concept. So this force F1 here is described only within the Y and Z plane, and that can be clear from the shaded area here. Furthermore, we use our 3, 4, 5 triangle to describe that, just to practice that again. So this is something that, while new to some students, can actually be easily implemented with a little bit of practice. The thing that's brand new is usually the way this one is described. And now be very careful. F2 has a magnitude of 800 pounds, and it has some angle of 45 degrees and some angle of 30 degrees. These angles are not cosine, alpha, beta, whatever you want to call them, right? So these are not the directional cosines. This is a 45-degree angle that projects the force onto the xy plane, and I will explain that more when we solve the problem. And then this 30 degrees projects the projected force onto the x and onto the y plane. And that is why students in the classroom usually choose this problem as being more difficult, and why we focus on that one in the classroom. So let's go ahead and describe our forces. Maybe it's best if I do that right next to the picture here. So let's say that F1 is really equal to 500, and now it has no I component, so 500 times 0I plus some J component, and that J component really is 4, right? So it's 4 over 5 J plus, because it's upwards acting, 3 over 5 K hat. So that is the base description of our force number 1, and for now I leave it that way. Now for my other force, for F2, it's probably best to use geometry or to zoom into our problem. So I'm going to do that here, and I'm going to grab my ruler. And the first thing that I want to calculate, the very easiest one, is the vertical component. So I'm going to make that purple here. So the vertical component, that would be equal to 800 pounds times sine of 45. And I'm very well aware that sine and cosine of 45 is the same thing, but I purposely picked sine here because it's on the opposite to the 45 degree. So that force here can be described by that value, and of course we know that that value must go down. And if I punch that into my calculator, I end up with negative 565.8. So 565.8, and that is in pounds. Now the more complicated part, or seemingly more complicated part, which is the force on this diagonal, that is only an intermediate force. In fact, I'm going to call this force F2 xy, because it's the F2 xy component that pretty much acts in the xy plane. It's not something that we need for our answer, but it's something that I first have to calculate. And that would be equal to 800 times the cosine of 45. And I won't even really calculate that, because what I'm really after is the x component and the y component, and the xy force is only an intermediate value. So what I really need is this force here, and that is just 800 times the cosine 45, which is the component that I just calculated in green, multiplied by the cosine of 30. Because once I have the green line here, I can just project it onto the blue line by cosine 30. And that is my value for F2x. And a similar method I can use to calculate my y component, which would be right here. However, I find it much easier to show it down here, which is also in the y direction, because now all I have to do is project the force, the green force, onto that red line. So let's do that. So the value here would be F2y, which would be equal to 800 times the cosine of 45, multiplied now by the sine of 30. And that value will give me F2y. This is something that initially might not be the most obvious way to look at these problems for students. However, I think everybody in this class who really, applies themselves will understand this and easily apply this in their homework problems. And I think I just showed you how to do this, so now I can move on to really calculating my values. So my F2 now would be something like the x component, which is what, 800, I can factor that out. So 800 times cosine 45 times cosine 30 I hat plus cosine 45 times sine 30 j hat plus, well, actually I have to be careful. It's a minus, so minus 800 times sine 45. And that is k hat. And all of this is in pounds, which of course I kind of forgot up here, so minus points for me. And now all I have to do is calculate the real values. So for example, if I do that for f1, I would end up with something like 0 I hat plus 400 j hat plus 300 k hat. Very clear numbers. You see that I don't even need a calculator for those. That is different for the next one. I definitely need a calculator for that one. But what I will find here is that I have 489.9 I hat plus 282.8 j hat minus, that is important to keep in mind, 565.8 k hat. And all of that in pounds. Now, last but not least, to find f resultant, I have to find the sum of f1 plus f2. And of course, I shouldn't forget that these are vectors. So now all I have to do is combine the I, j, k components. So let's go ahead and do that. So we find that the I component remains 489.9 I hat plus, now I need to combine the two, 682.8 j hat and minus 265.8 k hat. And that now is a real answer in pounds. And since it's a real answer, I need to double underline it. Provide my answer error. But I am not done, because remember, we always need to identify three entities. So my next thing that I need to calculate is f res magnitude, which of course is nothing else than the combined squared sums. And I prefer to actually raise it to the power of 1/2, because that's the same as the square root if I have such long expressions, so I don't have to draw such a long square root. But the answer, of course, is the same, and the answer in this case is 881.4 pounds. And once again, it's an answer, so I double underline, and I provide my answer error. Now I'm still short on one result, and you guessed it, that result would be alpha, beta, gamma. How do I calculate alpha, beta, gamma? You already guessed it. It is alpha, for example, being the cosine inverse of fx divided by f, right? So if I do that for alpha, I will find that the cosine inverse of 4899 divided by 8814, and that is really equal to 56.23. And if I do the same for beta, I will find that I end up with 39.22. But for gamma, I have to be extremely careful because I am now looking at a force that is actually negative, which means it's downwards in the z direction. And therefore, I would have a negative component here, which sometimes some calculator handle really well, but others don't. You definitely have to end up with a value that is 101.5 in this case. And that needs to be handled very carefully. In fact, you want to do your final conclusion or your final test, which is equal to cosine square alpha. So this is 56.23 plus cosine square beta, 39.22 plus cosine squared 101.5. And that needs to be equal to 1. I think this is equal to 0.9 something, 8 or so. But that is close enough to 1 so that we can be sure that we calculated the right value. However, please do really run this test at the end of your numbers, because often you will find that you didn't use this negative value correct, or I should say this negative value correct, and that you had a problem here then, and this formula will reveal it, so that you don't move on the exam with an incorrect answer, or even worse, in real life, you move on with an incorrect answer. So that definitely is a must at the end of each problem to check your answers. In fact, that's the nice thing about engineering mechanics, that you're always able to double check your answers because you have multiple ways to arrive at the same result. So this concludes this problem. Let's take a look real quick at this problem here because it's so much fun, and this one actually is easy. But let's, for completeness reasons, do that as well. So for example, here we need to have F1 plus F2, which is the F resultant. This is not different from the other one, except that now it's given to us. So F resultant is really equal to 0 I hat in F1, 0 plus 50 from F2 I hat, plus minus 100, be careful here, plus 60 j hat, plus 100 plus 80 k hat. And you see it's actually fairly easy numbers. You don't even need to get out your calculator. However, the answer here would be equal to 50 I hat minus 40 j hat and plus 180 k hat. That is all given in pounds, and it is a result, so I better double underline. And now I of course have to calculate my resultant magnitude, which is nothing else than 50 square plus 40 square plus 180 squared, and the whole thing square rooted, which is the same as to the power of 1/2, and that is really equal to 191.1, if you will, pounds. Once again, a result. Let's double underline it. And last but not least, I need to calculate my angles. So alpha would be equal to cosine inverse of 50 divided by 191.1, whereas beta is equal to cosine inverse of, be careful, it's a negative 40 divided by 191.1, and that will cause a very different result, similar to what we've seen before. Gamma is equal to cosine inverse of 180 divided by 191.1, and the answer to these problems is 74.83 degrees, 102.1. This is a dangerous one because if you would have used positive 40, you would actually end up with 77 point something. And that is not what we're looking for here in this case, because that would be the wrong beta angle in this case. And the last one would be 19.62 degrees. And now, last but not least, I have to test that again by saying cosine squared alpha 74.83 plus cosine squared beta 102.1 plus cosine squared 19.62, and that better be equal to 1. And we are done with this problem as well. Of course, I need to double underline my results here, but that completes the entirety of these two problems, and I believe we now have a solid understanding on how to use these problems and also how to interpret them. Always pay attention to your positives and negatives. Sometimes it's best even to redraw a result sketch. Be sure that you understand how to interpret these different angles and how they're given to you. For example, the most important thing is that you need to understand how to differentiate between these given angles and alpha, beta, and gamma. So this is different. I explained that at the beginning of the problem. Make sure that you understand that, and also that you understand how to look at these problems in a 3D system. So see here's even no shaded area, but the dashed lines indicate that this is only acting in the YZ plane, whereas this one here has dashed lines in all directions, so therefore it's in the XYZ plane. So that is completely solved examples now, and with that said, we can now move on briefly to position vectors, because that is also part of your homework. You will see that the mathematics is the same, but we are now done with examples for force vectors in 3D.